All right, so now we're going to be talking about exponential decay functions. So I've just shown you here, I've kind of given you just a little reminder. Exponential growth functions are going to have horizontal asymptotes, and they are going to increase very quickly forever. Exponential decay functions are still going to have an asymptote, see that they never hit there, but they're going to be decreasing very quickly. That's the idea of decay. When we think about the pattern or the rate that we're going to be seeing, for growth, this is when you have a number that's greater than 1. Usually whole numbers are going to cause an increase. And then decay is when this value is going to be less than 1. So specifically, we said that was when you were dividing over and over again, or when you had a fraction. So this is r is less than 1. You may want to make a note that this is for fractions. And then you can put in parentheses that this is division. That's how you all kind of like to think about it. Remember from your previous lesson that really the number one thing that I need you to remember is this last value out here, whatever you're adding or subtracting at the end, is your horizontal asymptote. That's what you need to remember from that. And then I wanted to make one note. I don't know that I did a great job of touching on this in the other video, so I just wanted to remind you, exponent shortcuts, this is what we're going to use to graph, is because these are exponents we know really easily. So anything to the 0 power, no matter what it is, a positive number, a negative number, a fraction, anything to the 0 power is 1. So these all equal 1. That's why we like to have something to the 0 power, because it makes it easy for us to think about in our minds what the value will be. Anything to the 1 power, so we're talking here in the middle, is itself, because you just have one of those. So these are 2, -5, and 1/8. All right. Anything to the -1 power. So when you have negative exponents, this is something I haven't really done a great job of talking to you all about this year, but you did cover it in Algebra 1. Negative exponents are reciprocals. So remember, a reciprocal flips something. So instead of 2 to the negative power, it becomes 1/2. -5 to the negative power becomes -1/2. And then if it is a fraction, like 1/8, when you flip that, the reciprocal is a whole number 8. So today, the ones that are going to come in most handy are to the first power, and then things to the -1. Okay, so let's look at 2 quick graphing examples. Remember from your video yesterday, or your previous video, that this right here is your asymptote, and it is a horizontal asymptote. So at 3, we're going to draw ourselves a horizontal asymptote here. And then yesterday we wanted this exponent to be 0, because that would make it 1. So 0 is an easy exponent to have when you have a fraction. All right, so I'll start there, and then I'll explain what the other one should be. So if we have 0, that's option number 1, I'm going to have negative parentheses 1/10 to the -1 is actually the power that I need to use there. So let me make that correction. This is not 0 I'm plugging in, it's -1, so that my exponent becomes 0. Plus 3. All right, so that is negative 1/10 to the 0 power plus 3. Remember, anything to the 0 power is 1. I'll just say it over and over and over again. Plus 3, so this is -1 plus 3, which is 2. So this means when x is -1, I want to plot the value 2. So at -1, I'm going to plot the value 2. All right, now let's pick a different value. And because this is a fraction, I actually don't want to keep the fraction. I want to change it to a whole number. So to do that, I need my exponent to become -1. All right, I need my exponent to be -1. So to do that, I would need x to be, so we just kind of have to think what would make x do that. If x was -2, that would be the case. All right, so I'm going to have -1, parentheses 1/10, -2 plus 1 plus 3. All right, so remember that this negative right here is going to cause a reciprocal to happen. So instead of being 1/10, this is now going to become 10 plus 3. Well, that's something that's really easy for us to work out. Negative 10 plus 3 is just going to be negative 7. So that means at right here at x is negative 2, we want to plot the point negative 7. And I don't even actually have that on my graph, so I'll just kind of estimate that will be somewhere down here. And then we're just going to connect, and it's going to get really small really quickly, but never cross that asymptote line. All right, let's look at one more. Okay, still going to start with our horizontal asymptote. So that's going to go through negative 4. So we're going to draw our asymptote there. And then the first thing we do is we always want that to be 0. So that's going to be x is negative 2. That's the value that will make it 0. So if I plug that in, I've got 3 1/3 to the negative 2 plus 2 minus 4. 3 1/3 0. Anything to the 0 power is 1, so that's just 3 parentheses 1 minus 4, which is 3 minus 4, and that's negative 1. So at x is negative 2, I'm going to plot the point negative 1. All right, and now remember, because I have a fraction, I want to get rid of it. I need a negative exponent. And to make that exponent negative, the easiest thing to do to make it negative 1 is to pick the value x is negative 3. So we're going to do 3 to the 1/3 to the negative 3 plus 2 minus 4. Right, negative 1 is going to cause a reciprocal, so instead of 1/3, this is going to become the whole number 3 now. And then that's easy to multiply, 9 minus 4, which is 5. So at negative 3, I'm going to plot the point 5. And I'm going to draw a curve. It's decay, so we want it to get really small really quickly, but never hit that asymptote line. Hopefully that exponent stuff makes a little bit more sense this time around. Okay, the last thing we're going to do is to write equations for exponential decay from word problems. Now remember, I'm going to be using this format in the middle, so you may want to write down that this is the format we use for decay word problems. But what is different is you may notice that this is 1 minus. So when it was growth, we would do 1 plus whatever the rate was, and now we're going to do 1 minus because it's decay. We want it to get smaller, so we're going to have to use subtraction. If you want it to get bigger, you're going to have to use addition there. So we just want to identify our A is our starting point, just like it used to be. So if I read my problem here, A is going to be 28,000 because that's the original value. I need to identify R. R is our percentage. Remember that we want to write the percentage as a decimal, and I didn't really talk about that yesterday as much, but remember we got to move the decimal 2 places. So here, the R I actually want to use is 0.095. And then T, or N, or X, whatever you put as the exponent up there, I'll use T since that's what the book has right now. T is the time. So whatever the time is. And since I don't know T, I'm actually just going to leave it blank on mine so that we remember that's something we need to figure out. Okay, so if we're going to write our equation then, our equation is going to be, we can either say y equals or f of t. I'm just going to say y. All right, so y equals 28,000. And then we're going to do subtraction because if you read the problem, it says decreasing. That's how you know this is the decay problem. So subtraction 0.095 to the, and I'll even use x, to the x power. Okay, if we wanted to simplify that before we solved anything, we could say y equals 28,000. Okay. Now the problem is saying, when is this going to give me a value of $5,000? Well, this variable up here is how long this is happening, and I don't know the variable, so I can't plug anything in. So now I'm going to have to get my calculator out and see if I can help find the answer in there. Okay, so I've typed my equation into y equals, and I'm looking for when this will be $5,000. So it looks to me like the value hits $5,000 somewhere in between 17 and 18 years. All right, somewhere in that time frame. So I'm just going to say that that's going to happen between 17 and 18 years. All right, that's all we've got for today. Hopefully this one was a little bit easier than when we did the growth functions.